Alright, good morning, everyone. Last time we started talking about bearings, types of bearings, and we basically started covering the analysis and design of two main types of bearings. One with the curved surface, whether it's spherical or cylindrical, and we went through the equations for the AASHTO equations for the design, checking the pressure and checking the horizontal resistance of these bearing types, and we went through an example. And then after that we started to talk about a very common type of bearings, which is the elastomeric bearings. So we started an example. This was basically a bridge, two-span bridge, 130 feet each span, and I gave you a bunch of given data. Some of them are coming just from records, or some coming from the analysis that you had to do prior to reaching that point. And that's very important to understand, because you probably need to do this to come up with these numbers. For example, when we talk about the reaction here or there for live load or dead load, that's something that you should come up with from separate analysis, as you probably would do in your project. And then we started the first few steps, which is basically looking at the movements. So we said there are like temperature movements, there are like shrinkage for the girder, elastic shortening due to post-tensioning, and so on. There is shrinkage. And then from that, we're able to come up with a thickness and number of layers. And we said n equal 5, n being the number of interior elastomer layers or rubber layers. And we have for this a thickness of HRI. The two outer ones are usually thinner, with half of that thickness. So in total we have 7 layers, including the two top and bottom ones. Each layer has a thickness of 0.8 inches. So that's basically coming up with the thickness of 4.8 inches. Now let us move on and keep going to continue the example with step number 4. And in step number 4, we're going to come up with the bearing size now. Okay? So coming up with the bearing size. Basically, if this is the bearing, then we have a length L and a width W. So we're trying to come up with the dimensions of the bearing. We came up with the thickness. One important factor here that you can think of as related to the stiffness of that bearing is this shape factor. And maybe some of you have heard of it already in other courses. But the shape factor is an important parameter, and this is per layer. We're going to call this SI, shape factor, because it defines the stiffness of, or the rigidity of that layer of elastomer. So this would be LW divided by 2 HRI times L plus W. So this is the shape factor, this definition of the shape factor, expression for that. So we're going to be using this, and AASHTO refers to this a lot when you are picking the dimensions, and because it's the main parameter. You might change the L and the W, but you end up with the same shape factor. And what research have found is that theoretically you should reach the same performance, the same stiffness, the same deflections, regardless of what the L and the W is, as long as when you combine them together, you end up with the same shape factor value right there. So that's the point right there. It's one parameter that describes the shape. If you look in AASHTO, in sections 14.7, 0.6, 0.3, 1.2-7 and -8, you will find that as a requirement, we would say that the average compressive stress due to total loads, I should say here service loads. I'm going to put two lines under the word service, so you use the load, service load combinations. Sigma S should be smaller than or equal to 1.25 G, it's the shear modulus, we have given that early on, times SI. That's here where this SI comes into play. And this also has to be smaller than, and it does not exceed 1.25 KSI. So this is the compressive stress coming from total stress, dead, live, everything, coming from all loads in service load combinations or service state. So that is a requirement. So this is going to be governing our design for the bearing. Now, as a definition here, the sigma S is equal to the reaction divided by the dimension, LW, width, length times the width. And this would have to be equal to 1.25 G. And now I'm going to substitute for the SI from the previous expression we have, which is LW divided by 2HRI L plus W. So this is how we relate the sigma S with the L and W. Now at this point you have two variables. You have one equation, right? So the L and the W, those are two variables. So you will have to go through a trial and error process. So again, we can use, for example, using trial and error, we can try, for example, L equal 12 inches and W equal 18 inches. Now, you might be surprised that the width is longer than the length, because the width, actually, there is more room for actually the bearing to go in the width. But in the longitudinal direction, the pier actually thickness governs, or the abutment seating area governs that length. So when we say the length, we're talking about the longitudinal direction of the bridge, or direction of the traffic, if you will. Okay, so I can maybe start with these values and calculate my SI per layer. So that's going to be 12 inches, okay, times 18 inches divided by 2. The thickness of each layer is 0.8 inch times 12 plus 18 is L plus W. And the answer here is 4.5. And it's dimensionless. The shape factor is dimensionless. No units. Okay, so we end up with SI from this expression. Now, we wanna compute the sigma and the stress and the strain, corresponding strain from that. So step number 5 is, before we move on, any questions, guys, about this? Step number 5 is compressive deflection. Okay, now we know the stress, so we want to look at the deflection now. So the sigma S is, you add all the reactions from the dead, 155, from the live, 50, divide by the LW, so that's 12 by 18, and the answer is 0.95 KSI, which is smaller than, of course, less than 1.25. But is it less than this expression of 1.25 G LW divided by 2 HRI L plus W. If you substitute here, you will end up with 0.98, so it is less than that, so it's okay. So we chose an L and W that would satisfy this requirement. Okay, it will be smaller than the 0.98. And then, you know, after that, you would be actually getting the deflection from the strain. So we have a stress, and to be able to get the strain from that, we need a stress-strain curve or relationship. And that's also provided in AASHTO. So let's just take a quick look at, let's see here. Just a second. To open the bearing document we have here for AASHTO, and then we scroll down a little bit. Okay, here we go. These are curves provided in AASHTO, okay, that shows the relationship between in the vertical axis here you see the compressive stress, and the horizontal axis you see the compressive strain. And these curves, each one is corresponding to a specific shape factor, 12, 9, 6, 5, and so on. And here you will find two curves based on the durameter. The durameter is a value that measures the hardness of the rubber you are using. So this is a property of the rubber. So you have 50 durometer, you have 60 durometer down there. So basically that is a way for describing the hardness. And all what you have to do now is, using the compressive stress, go there, pick your shape factor. You can do interpolation between the curves, obviously, and then you go down and read your strain value. Okay, so that's what we're going to do now. So if you go back to our solution here, I'll write down that using figure C14.7.6.3.3-1, that's the figure we just looked at. Given this stress value, you will be able to determine the strain value, and you will find it roughly to be 0.064, coming from or corresponding to that stress of 0.95. Okay, so this stress will cause compressive strain per layer of that much. Now, to come up with the full deflection in compression, that's the delta, I will need to sum up all the strains from, the strain times the whole height, sum up of the height of these layers. So the summation of the epsilon I times the HRI. So we said we have 5 layers plus 1/2 on the top, 1/2 on the bottom. So I can count these as 6 layers of 0.8 inch thickness each. So I can just write down here 6 layers times the strain per layer times the thickness per layer of 0.8 inches. So that roughly is going to give us about 0.3 inches. So I'm expecting under service conditions, when we have full live load, we are expecting a compressive deflection or deformation of 0.3 inches. Why this is important? Because the deflection, actually, we're going to use it to determine the capacity, rotational capacity that's corresponding to this deflection. The more the deflection, the more rotation we can have. But if you don't have much deflection and you are actually rotating a lot, that's going to actually cause instability. So basically, the way we do this is, so this takes us to step number 6. Before that, any questions, guys? Okay, let's discuss here the maximum rotation. And that's step number 6. I'll just write down here that the rotational capacity theta, I will just call it theta capacity, is equal to, if you have, here is the bearing, okay, and at the center point of the bearing you are expecting a displacement downward of the amount delta that we came up with. That if you try to imagine how this thing rotates, this is the angle theta capacity, okay? So basically I'm taking this as 2 delta now, and this as my L, which is the length, right, of the bearing that we decided already or came up with. So from that, I'm expecting a full rotation of 2 delta by L. This is our capacity. This is the maximum that this thing can go, considering how much deflection it undergoes, right? Okay. So let's just substitute here. So that's 2 times 0.3 divided by L. We pick 12 inches. And the answer is 0.05 radian. Now, this capacity is greater than the theta design. Theta design, if you go back in your notes, it was given to you. And this theta design came from your regular analysis, okay? From, you know, based on the structural system. Now, everything we're doing here, by the way, it did not, you know, the analysis of the compression, everything, we did not look at what system. Is it a beam deck system? Is it a box girder system? Is it, you know, steel? Is it concrete? We don't know. We're just looking at the bearing. But in your theta design, when you are analyzing it, that's something that's going to come from your analysis of the system. And that showed, in this case, this to be equal to 0.25. That was given to you earlier in the notes, in the statement of the problem. So obviously, our capacity is greater than what the analysis shows, so we are okay. That is a good result there. Any questions, guys, about this? So now we have checked the rotation, okay? We have checked the vertical compression, right? All right. Step number 7. After we have done all this, one last important check we need to make that AASHTO provides is the check of stability. Given all the thickness and the dimensions now that they are given to us, what would be, is it stable or not? So I'll just write down here for you to remember that bearings shall be investigated for instability at the service limit state load combinations, or at the service limit state, and I'll just leave it there. You know that we have to use the load combinations for the service limit state. Okay. And how do we do this check? There are different ways of doing the check, but the simplest way that AASHTO presents is using the simple inequality. 2a has to be smaller than or equal to b. Okay, what's the a and what's the b? These are parameters that are dependent on the geometry, mainly. So the a is 1.92 HRT, that's the total thickness, divided by L. Everything is divided by square root of 1 plus 2 L by W. Okay, so that's it. So let's just substitute with what we know. So that will be 1.92 times the full thickness is 4.8 divided by the length of 12 inches. divided by the square root of 1 plus 2 times 12 inches divided by 18 inches. And the answer here is 0.5. We got the A. Now, let's look at the B. And of course, you know, there's a lot of references if you're interested to know more about where these expressions came from and the research behind them. You know, there's a lot of references there that you can find for these stability checks for the bearings. Okay, now B. B is 2.67 divided by SI plus 2 times 1 plus L by 4W, and you close the parentheses. Okay, let's just substitute now with what we know. So 2.67 divided by 4.5 plus 2, 1 plus L is 12, divided by 4 times 18 inches. And the answer here is 0.352. Now, just by looking here, this is the check. 2A should be smaller than or equal B. Now, just by looking, it doesn't seem to be working because 2 times A is 0.5, which is 1, is greater actually than B, which is 0.352. So that's not good. Okay? That's not good. In this case, what should we do? Well, in this case, it doesn't mean totally that you are gonna have to change the design. There's one more layer of check because everything we're doing now, by the way, does not depend on the demand. So what if we have a very low demand on the bearing? Even if this check did not pass, because of the low demand, it might be okay to use it. But if this check did not pass and then you have high demand, meaning high compressive stress on the bearing, then maybe you ought to change the geometry, okay? So to do that, to check now introduce the demand into the picture, I'll just say here that if not okay, then we ought to do this coming check. Okay. The check has two forms. The first is checking that the demand sigma S is smaller than or equal to the GSI divided by 2A minus B. And that is used for deck that is free to translate horizontally. Okay. What if not? Well, the second form is sigma S should be smaller than or equal to GSI divided by A minus B. Basically, if the deck is, or the superstructure is allowed to move horizontally, you are of higher risk of instability. So it's more strict there compared to the one below. The one below, because already we're constrained, we're not allowing this to move, then there is a little bit less risk of instability. So this is for the case with the deck being fixed against horizontal translation. Horizontal translation. This is very important. Okay. So now, given our problem, if you go back to the bridge, you know, we had like a pin here, we had a roller here, we have a roller here. This is how the bridge looked like. So do you think we fall into the first or second category? Deck free to translate or not? Based on this, you know, given info right there.
The bearing at the middle should be fixed.
Mhm.
The end should be fixed.
Right. So basically, if we're designing, you know, the bearing, I'm worried about the movement here. So it's considered free, right? Even the one in the middle is not, you know, movable, but still these ones are going to move. So the deck, at least this half is going to move. So maybe when I'm designing this bearing, I should not consider that. I could just go with the one that is actually constrained from movement. But if I want to use the same type of bearing, that's a different story. Then I would have to go with actually the one that's more conservative, which is the one that can experience horizontal translation. So meaning that I'm going to go with this one right there. So let's do the check and see if our demands are high enough to cause us to do the shape and the geometry or not. So for this, I'm going to take this expression, which is the sigma s smaller than or equal to GSI by 2A minus B. And let's substitute. Sigma s, we have calculated that already from before, which is 0.95 KSI. G was given to us as 0.175 times SI, we calculated this as 4.5, and we know the A and the B. A is 0.5, B is 0.352, and the answer is 1.215 KSI. So definitely that's small, so we are okay. We are okay. So the demand is not high enough to make us change the design. What if it was high? Well, I have no other option but to change the L and W and thickness and all this kind of stuff to make it work. So you got the point. Any questions, guys, about this? Yes.
Can you again explain which, like, what the directions L and W?
Sure.
In respect to, like.
Sure. L is in the longitudinal direction, this direction of the bridge. Okay. W is in that direction, right there. So this is L, this is W. Other questions? Okay, so far we have been talking a lot about the elastomer, the rubber part of the bearing. There is steel part, remember, that's reinforcement we are providing there that would eliminate or reduce, I should say, the bulging of that rubber and providing stiffness. So last step in the design is to come up with the reinforcement. So that's step number 8, reinforcement. All right. The reinforcement is in the form of steel plates. Steel plates. The minimum thickness as per AASHTO for the steel plate that you should use in these types of bearings is 0.0625 inches. So that's one important piece of information. Now, as we said, we are going to check this under service limit state. So at service limit state, this HS should be greater than or equal to 3 HRI, that's the thickness per layer, times sigma S divided by the Fy. So let's check. So it should be greater than or equal to 3 times, the thickness per layer is 0.8 inches, times sigma S, we have done this already under service conditions, dead plus live load, give us 0.95 KSI divided by the Fy was given to us at the beginning of the problem, which is 50 KSI. So the answer is 0.046 inches. To satisfy the surface limit state, the thickness should exceed 0.046. Because we're talking about steel, and these bearings will be subjected to high number of cyclic loading, right? Vertically and horizontally, under traffic loads and vibrations, wind and so forth. So fatigue is an important issue here. So we have to check fatigue. So at fatigue limit state, the HS should be greater than or equal to 2 HRI sigma L. That's the live load only. Remember, when we're talking about fatigue, dead load doesn't really matter much. It's the live load, because that's what's the cause of the fluctuation of the stress. So we only consider the live load in this case. Divide by the delta FTH, which is the threshold for the fatigue limit state load combination 1. There are 2 of those, right? That's the first one. Okay. So we need to calculate the sigma L. I don't think we have done that before. We know the sigma S, but not the sigma L. So the sigma L is equal to 50 kips divided by the dimensions we got, 12 times 18. So that is 0.231 KSI. Let's plug it in here. So the HS should be greater than or equal to 2 times 0.8 times 0.231 KSI divided by the delta FTH was given to us as 24 KSI. And the answer we get here is 0.015 inches. 0.015 inches. Now, out of all these 3 values, remember, the absolute minimum value is 0.0625. The one from the service limit states 0.046. The one from the fatigue is 0.015. Obviously, this one governs, because that's the highest one out of all 3 values. So in this case, I'm going to use this as my minimum thickness there for the steel plates. So I'll just say here, use HS equal HS min of 0.0625 inches. Okay, so now I've determined the thickness of the plate. Then we're done. Practically, we're done. Let's just give you like a summary of what we have done here with the final design and everything. So basically, we are having like, bunch of like, this is how the bearing would look like. We have like 7 layers. Okay, and we could write down here that this is our final design. We have in total 5 interior layers, 0.8 inch each. We have 2 exterior layers of half of that, 0.4 inches each. And in between the 7, now it has 7 rubber layers, right? There will be 6 steel plates. So 6 steel layers of 0.0625 inches each. And the bearing size is 12 inches in length, 18 inches in width. And just to clarify that, by width here I mean the transverse direction, just for clarity. The width here is in the transverse direction. perpendicular to the traffic, if you will, or not in the same direction of the traffic. And that concludes our bearing design. I think that's a good amount of information I covered, between this type of bearing and the previous type. That should give you, good idea about how we do bearing design in bridges, and also for your project. So that's something that is going to be important for you to apply. All right. So as a reminder, our midterm is this Thursday. Okay. What I'm going to do is, as I said before, I'm going to post you're going to get access actually to the exam on Compass 2G. What I'm going to do is that I'm going to basically, since we're not going to have a class, I'm going to use the time for the class for those students who wish to use that towards the test. So I'm going to start it at 9:30 or so. Okay? So you'll be able to get access to the test online at that time. And then I'll leave for about 12 hours or so. Okay, a window of 12 hours. So if you have classes in the morning, if you have anything, maybe you want to finish your classes and then maybe start at 4 or 3 or 5 o'clock, you still have some time actually to finish everything, okay, before 9:30 at night or so. So that will give us a window of 12 hours, and then you'll upload your solutions on Compass 2G. The exam is open book, open notes, everything through homework 4. That you should have all the solutions now for homework 4, 3, and 2. And what else? Any questions from the 3 of you? I'm assuming there's a lot of questions maybe from others, but you're the lucky ones already here.
Is it open now the whole 12 hours, or do we just have the 4 hours still?
You have a total time of 4 hours. So you can, what I can do is that you can have multiple attempts. So, I mean, if for whatever reason you get kicked out, you'll be able to log in hopefully again. But the total time you have is 4 hours between all the logging in and out and all this kind of stuff. So, I would recommend you doing on one sitting. So that'll be the best in my opinion, if you just want to do it in one sitting. But there will be ability for you to, if you, for whatever reason it happened and you got kicked out or Compass shut down, that you'll be able to log in again and it won't completely, it won't submit. Okay? But you will have a full 4 hours of, time to work problems. And it's straightforward, should be very simple and easy, nothing really surprising there. So, yeah.
Is it just like to know like timing and stuff? Because I like have classes. Like, is this so designed to take the full 4 hours, or is it like?
No. I never took test designed to take the full time. No, because that would be unfair to some students. So, I think, in my opinion, it shouldn't take more than 2.5 to 3 hours. Should be like 3 hours, and then maybe 1 hour but whoever is a little bit maybe taking some time, they might use the full 4 hours. But I think it will be more like 3 hours, 15 minutes, something like that. Other questions?
You said like till homework 4, but the like topics like MCFT bearing abutments are not covered in.
They're not in the test. Not in the test, because. As I said, I always like to give you a chance to go through things in the homework first. That's a good way for you to practice, to figure out issues, problems that you can ask about. I think it's fair to do this before I put you in a test. These problems, I know that you might face them while doing the project, which is a good thing. So that satisfies me. That gives me the, the whole point of, you being able to go through it. And that's where I'm going to be looking honestly at, did you apply the MCFT or not in your project? That's a good thing. You applied correctly or not? You apply bearing design or not? Okay, so one of the students asked me, well, I have a software I found that can do everything for me. Perfect. I'm not going to be happy with that because my point, I'm not going to design this bridge to construct it. this idea is for you to, the whole idea is for you to go through the process yourself. Software, I know there are software out there that can just, you just give it the dimensions and pretty much it gives you everything that you need. But that's not the intention right there. That's not my intent at all. Okay? Let me just see. Oops. Just a second. Okay. We're back. Other questions, guys? About the test or anything else? Yeah.
So for the project, like the preliminary proposals, like due Thursday.
We're due Thursday, yeah.
Yeah, when can we expect like the feedback on that so we can like start the?
I'll be honest with you. As I said before, this should be the final thing. This should be after you get the feedback. So it's not like, hey, you know what? I'm gonna grade those and give them back to you and tell you. No. You should have done your homework prior to submitting this. This is the final plans that should have been finalized already. So I've had students, for example, last week who joined office hours and they started actually chatting with me a little bit about their thoughts, and some of them shared even slides. I like that because, you should be able to finalize your design through discussions. That's why I have to post it a little bit earlier for this project. But I don't think, if you still have questions, of course, after the 22nd, that's fine, you can still ask. But I'm gonna actually grade it based on what you have submitted on the 22nd. So that's the thing there. But if you still have problems or issues or facing questions, of course, you can ask anytime. But there won't be informal feedback like grading and stuff like this.
So with the preliminary proposal, like, are we supposed to have like the sizing of all the members and like all that design?
You can provide some reasonable sizing, okay? But I'm not gonna penalize you if you go and change that later on. It's not gonna be like, hey, cast in stone, you cannot just change that because you've already committed to this. No. But something reasonable, something within. I mean, when you tell me like I think we can use a pier size of, if it's a diameter of 4 feet, okay. But if you're going to tell me a 12 feet diameter, okay, no, that's a little bit unusual. Okay, so stuff like that. When you tell me, for example, a pre-tension, precast AASHTO type 1 goes 150 feet long span, that's a little bit ridiculous, okay? So again, stuff like that I want to keep an eye on when we're doing the prelim design. Avoid these kind of mistakes. But dimensions and reinforcements and detailing and all this kind of stuff, that will come later. Other questions? So, unfortunately, you have to submit both on the 22nd. My first inclination was to give you the midterm last week, but I know that you had another midterm last week, so I pushed the midterm to this week. But hopefully you can manage. After that's going to be only the project, and then you're going to be done with the scores. Okay? All right. Let us start now talking about something different a little bit, switching gears a little bit. I want to start going through a brief example. I won't go through the whole thing about concrete deck design. Okay? Because we kind of like rushed through it, and some of the details about the service limit states and stuff like that, I think we have a little bit, yes, we covered it, but we didn't go in much depth and details. And you will need to do that in the project. So I'm gonna try to go through an example here with you. What we're gonna be using here is the approximate method. Which is basically, sometimes we refer to it as the strip method. Okay? And you can find this in AASHTO 4.6.2.1. So let's just take an example. Again, as I said, I'm not gonna solve the whole thing because it's kind of lengthy a little bit, but I wanna use it to just give you some practical perspective of our discussion here, what we're gonna be talking about. I'm just going to assume that this is a bridge I would like to design. And the bridge, these are the barriers or so. The dimensions are given to you as the barrier width here, the base is 15 inches each. And in between we have a 44 feet width. It's the clear, span between the barriers. And we're having here the dimensions, the overhang right there is 3.25 feet, for example. And this is like 5 spacings or spans between the girders, 8 foot each. So that gives us 40 feet. These are beams, like it's shown here as cast in place, but really the application that we're going to do here of the methods that we're going to cover, they could be used for anything, like precast beam with cast in place deck, for example, or steel beam with cast in place deck. So really there's no really requirement for this to be fully cast in place or anything like that. So that's the geometry that we are starting with. All what I'm going to be focusing on is the deck. So I'm not going to do the beams or anything like that because we have covered already some examples in the past about the beams. So they're given information close this guys, try to look at the game. Okay. Let's say that you were given that you need to provide a sacrificial wear, okay, of 0.5 inches. Meaning that part of the deck would be sacrificial, and that would be 0.5 inches. Okay. On the top of the deck, you will provide future wearing surface of 3 inches. And that could be, as we said earlier, made of like bituminous or asphalt material. And the density or the gamma for this material was given to you as 0.14 kcf. So you were given the density or the weight per cubic volume of that material. The barriers had a weight of 0.32 kip per foot. Okay. And the barrier CG is 5 inches from the external face or exterior face of the bridge, so the edge essentially of the bridge, And the F prime C is for the deck is 4.5 KSI, and the Fy for the steel used is 60 KSI. So you're given this information. This is pretty much what you would typically need to design the deck. These are the information you typically need to design the deck. Now let's start the solution. See what are the steps that you should take when you are designing deck. Number one, come up with the thickness, obviously. Come up with the thickness. Well, if you look in AASHTO, typically you should not go below 7 inches. So as per AASHTO, the minimum slab or deck thickness is 7 inches. And this you can find in section 9.7.1.1. Okay. So including the 0.5 inch sacrificial wear, okay, that would mean that I would go with H-min of roughly 7.5 inches. I have the 7, and then, you know, I'm not gonna count the 0.5, I'm just gonna add it on the top of the 7, so that's give me 7.5. So I'm just gonna go ahead and choose, round it up to 8 inches. So I'm gonna go with 8 inches as thickness. And typically we don't see a lot of decks below that that value, that thickness value of 8 inches. So that's the simplest thing you can do, just starting with that. Okay. Sometimes we find that depending on the overhang and the design, sometimes we provide higher thickness for the overhang. Because of the high deflection, everything, we want to provide a little bit more stiffness. So for the overhang, either, and this is an advice also for you in the project, either use the same or increase by something in the range of maybe 1 inch or so. So for this case, for example, I'm going to choose the H overhang to be equal to 9 inches instead of 8. Just, you know, or sometimes you just keep it the same. So in this particular case, I'm going to go with 1 inch in addition to the 8 inch that we have for the deck. We came up with the thickness. Okay, any questions? We start calculation of the dead load. So that's step number 2. Dead load calculations. Well, for the slab itself, that's going to be like 8 inches. I'll convert it to feet by dividing it by 12. And I'll multiply it by the density or the weight of the concrete per cubic foot. Let's say it was given to you as 0.15, for example. I know sometimes we use 0.145 for AASHTO. Let's just say that it was given to you as 0.15. And that will give us 0.1 KSF. Of course, here, this is for the interior spans, not the overhang. The wearing surface, also the asphalt. So the dead load for that, we have 3 inches as thickness. I'll divide by 12 also for the units. And I'll multiply by its weight per cubic foot, which is 0.14. And this will provide us with 0.035 KSF. So we got the weight for the interior span and for the weighting layer or surface. And then also I'm going to provide the WS, but for the overhang, so that's going to be 9 inches by 12 times 0.15, and that is going to be 0.113 KSF. So this is also for the overhang. The other dead load that we should consider also is the barrier weight, and that's a point load, or a line load, if you will, along the bridge edges. So the P barrier, that is given to us already as 0.32 kips per foot. So now we got, all the dead loads that we should consider in the load combinations we have, and we calculated them. So now we need to move to step number 3, which is the dead load bending moments. Now, if you look at the load combinations, there's of course a term for the dead load and term for the live load. So you treat each one separately and then you combine them in the load combinations. So let's start with the dead load moments first. I'll just write down here that under uniform load and unit width strip So we are doing this calculation assuming uniform load and unit width of the bridge. So everything is going to be per linear foot. So for example, when you look at the dead load, how it's being laid on or placed on the bridge, we have the overhang, we have 6 girders, 1, 2, 3, 4, 5, and 6. Okay. The overhang has a little bit higher uniform load because of its higher thickness of 9 inches. And that is 0.113 KSF. There's also point loads here and there, which is the barrier, placed at the CG of the barrier, which was given to us, if you recall, at 5 inches from the edge. So that's where the centroid, where the line of action of this weight of the barrier is. And this is going to be 0.32 kips per foot. And then, of course, we'll have a little bit lower value for this uniform dead load on the interior spans, and the value here is going to be equal to 0.1 KSF. So this is how the dead load look like. Of course, you got the dimensions and everything, so we know what the dimensions are. All what you got to do now is plug this into a software and just solve it to come up with the moment diagram. And if you do this, you will end up with, I'm just gonna just show part of the moment diagram just to give you a sense of how the results is gonna look like. So again, here is the beams. And you will end up with something maybe like this. This particular case, you might end up with something like that. this, and so on. You got the idea. And it's symmetric, of course. The good thing about it, it's symmetric. Well, we got the reactions here, 1.24 kips, 0.61 kip. The value here is 1.5, 0.28, 0.58, and so on. Here, 0.38, and you got that. Here's almost touching there. It's almost zero. So this is how the moment looked like under the permanent dead load. So we treat the barriers as part of that permanent dead load. Any questions, guys, about this? So these are steps that, as I said, you probably have to go through it when you're doing the deck analysis. Now, why can't I include the wearing surface here? I only included the self-weight of the beam, of the slab. Can somebody tell me that? Why I did not include the, go up here. I did not include this WDW, which is the dead weight of the wearing surface. Any guess?
During the construction process, so this will be provided like after the.
Sure, it's going to be provided after, but now what I'm doing is that I'm calculating the dead load moment.
This will be taken by the girder as the composite section.
The wearing surface? So I don't have to design the deck for the wearing surface? Is that what you're saying? Eventually it's going to go to the girders, I understand, but in the load path from up there to the girders, it's going to be carried by the slab. Like the self-weight. I mean, really, it's nothing more than just another layer there, right? It's just on the top of this, we have another layer there that should be sitting there with that thing. So why I neglected it here or ignored it? Again, that's why the steps, I want to go through these steps because these questions, yes?
Because it has a different load factor.
Very good. Yes. If you go back to the load combinations, the permanent dead load, okay, because it has less randomness in it, it has lower load factor. Can somebody remember that? Do you remember that? For the permanent dead load? It's 1.25. That's the one that I should be multiplying to these values right there. But for the wearing surface, it's 1.5. So it's higher. So I cannot just combine them together. I have to separate them. So they have, in bridges, we treat them like separate loads because of the difference in the load factors. Very good. So you guys understand this? Any questions? Okay. So let's just do now the second type of dead load, which is the wearing surface. For example, in buildings, we don't do that, right? We don't do this. They're all combined together. So that's one important difference in bridges. All right. This thing is not. Okay, so let's just try to draw the loads now for the wearing surface. Here are the girders. Of course, I have to exclude the part that's being covered by the barrier. And that is 15 inches at the end, here and there. So that has to be taken out, because the wearing surface is not going to be covering that. So I'm only going to be applying this everywhere else. Okay? and that will be 0.035 KSF. And if I want to plot the moment diagram for this, again, the same thing we did before. It's going to look more or less something like this. And so on. You got it. So the reactions here is going to be like 0.19 kips, 0.3 kips, so on. Here is 0.07, 0.22, 0.18. Again, just to give you a sense of how much the moments look like as a value compared to the value coming from the weight. Of course, the barrier actually plays a big role in reducing some of this positive moment there, because heavy point loads sitting right on the almost the edge of the overhang. Okay? Very good. Any questions, guys? Questions? Okay. So we're done with the dead loads and the moments coming from the dead loads. Now let's move to the live load, the vehicular live load. So that's step number 4. I will just say here, just to remind you that loads, or the load is placed in the transverse direction to maximize the load effect. So I have a very specific target and clear target here in my mind when I'm placing the live load. The vehicular wheel load is to maximize its effect. So you might say, well, I have to respect the lanes. No. This question I get all the time. Okay, I have like a 10-foot or 12-foot traffic lane. Should I only be like centering the load in the lane? No, of course not, because there are drivers out there that do not respect the rules of traffic, right? It might happen, be a drunk guy or whatever, So that's not going to be respected by them. So as a designer, you should take the worst case scenario. Okay, so that's an important thing. Few rules or guidelines that you would like to follow in designing the deck. For the wheel load, for example, the wheel load placement, it should not be smaller than this placement 1 foot or placed closer than 1 foot from the face of the curb or the barrier. Okay? Also, it should not be placed closer than 2 feet from the edge of the 12-foot design lane. Okay, this second, guideline is important when you are placing 2 trucks next to each other. You have to respect the room between, or the space between the wheels of both trucks. I can't just say, well, here's my bridge. Here is 1 truck, and here's the second one. No, you have to leave some clearance there between these 2. That's the point of having this 2 feet thing. So basically, there will be 2 foot coming from that truck, and then 2 foot from the next to it truck, the adjacent truck. That will leave at least 4 feet. So that translates into leaving at least 4 feet in the transverse direction, of course, between 2 trucks. Okay, so that's something that's also, and we have covered this already before, but I'm just trying to emphasize this again. As we have seen in the HL93, we have 2 options for trucks. We have the tandem, the heavy one, the 25 kip thing, and we have the HS20. Typically, HS20 governs here because of the heavier wheels in this case. So, but you may try both. So I just write down here that the design truck typically governs in deck design compared to the tandem vehicle. Tandem vehicles are always nice and useful when you're dealing with a very short span in the longitudinal direction, where you have no room for placing more than one axle of the 32 kip of the HS20, the 32 kip axles. So maybe having this more like a concentrated load would be a useful thing. Okay. Another thing here also is when you're placing the wheel load, you can put it as a point load or you can put it as a pressure. Realistically, it's a pressure because when you consider the tire contact surface with the road or the asphalt, it's pressure. It's not a point load. So as a designer, you have the option of doing it either way. So I'll just write down here that wheel load is either applied as pressure or concentrated load. Okay, as a pressure, concentrated load, that's kind of straightforward. But how about pressure? Well, here is how you follow the rule when you're applying this as a pressure. Let's say that this is the surface of the top surface and the bottom surface of the slab. You apply pressure like this, okay? And the pressure is pointing, of course, downward. This is the center line, for example, of the deck. The deck, let's say, has a full thickness of H. And in the other, so this is the transverse direction, obviously. In the longitudinal direction here, it goes like this. So this pressure is going to be the summation of the pressure, or the resultant of the pressure is going to be how much, guys? What's the wheel load there?
16.
16. Very good. 16 kips. So that's going to be a pressure that's resulting in a full load of 16 kips, the wheel load. It's distributed on a distance in this direction, the transverse direction, of 20 inches, and in that direction of 10 inches. So it's distributed this pressure on an area of 20 by 10. 20 by 10. Okay, good. In our analysis, we are actually looking at the center line of the deck. So we would have to assume that this pressure will travel with an angle of about 45 degrees or so within the deck until it reaches the center line. So now, based on this, I can just summarize that in a way that it's basically a pressure. Okay, with a resultant of 16 kips with a full length equal to 20 inches plus H, because I'm taking the assumption of 45-degree spreading here of the pressure throughout the slab or within the slab until it reaches the center line. So you are allowed, as a designer, to use a load like this instead of a point load. Of course, it's more realistic, maybe less conservative than the concentrated load, but that's okay, because it's more realistic. So you are allowed to use a pressure load like this. Sometimes we we tend to use this when we are, for example, checking the rating of a bridge, and we are tight a little bit on the the rating. I want to grab everything possible just to see if it's going to work or not. Be more realistic, in other words. Then we can actually go with a pressure distribution like that. Any questions, guys?
For tandem, it will be 12.5, right?
Yes, if you're going to go with the tandem. Yes. Yes.
When you said that the design lane, it can't be less than 2 feet from the edge of the design lane.
Yes.
Did you say it was 12 feet?
This is the traffic. Remember at the beginning when we said the design lane width is 10. But when you talk to the transportation folks, transportation engineers, they consider it as 12. So, in other words, it doesn't matter whether it's 10 or 12 because that will change depending on the width of the bridge. Remember, it could go as low as 8.5 or 9 feet. What is important from this, and that's why it's placed in AASHTO, is that you have to keep clearance between both trucks, assuming that each one occupies a lane, whether this is 10 or 12-foot lane. So that's typically what it is, that it should not be less than 2 feet from the edge of that lane. Other questions, guys? Okay, I think I'm gonna stop here now. Thursday, there's no class, obviously, because of the test. So we're gonna meet again on Tuesday of next week, and hopefully we can continue this next week. Thank you, guys, and I'll see you later. Take care.
That's a good question.
Sure.
So I got my homework before, but I was a little confused on the onshore case. For the onshore case, I considered the weight of the slab on the girder, and I got points taken off for this that shouldn't soon.
First of all, I don't think it's a problem. It should matter whether it's short or unshort because it was not given in the problem statement. So why did you even think of shoring versus
Because I
unshort?
went to office hours and then they told me that.
Okay.
You have to consider both.
I think it was a little bit off on this
Okay.
because it was not brought up in the statement of the problem.
Yeah.
So you would have to consider basically that the bridge girder carried the weight of the slab.
Yeah.
Yeah. So it's like an unshort case. And that's it. If other case of the short, that's not covered and should not be
Yeah.
mentioned.
So I don't know why.
Talk to the TA. I mean, my recommendation, since he's the one who graded this, if you have conflict with the TA after you discuss it with him, let's say he did not convince you, I'm not happy with what he said, come and see me, and I'm going to discuss it with you. But it might be something that he made a mistake.
Okay.
He might correct it.
I just want to make sure I didn't do a mistake.
But it makes sense that, if it's unsure, what you're saying is right. Deck's weight should be carried by the slab, by the girder.
Yeah. Okay. I will check that.
Okay?
Thank you.
Sure. by the way, I'm gonna let him know that he should not mark down anything or take points off because of the shoring thing, because it was not mentioned in the statement of problem.
Yeah.
If there's anything related to that and points you took out because of this, let me know.